Let's begin our discussion of thermodynamics in Chapter 1. What is thermodynamics? Well, the name of this course is heat power, and I just threw out the word thermodynamics, so you were tricked. You're in a thermo class. Oh my goodness, it's scary. It's not too bad. Thermodynamics actually comes from two Greek words, therm and dynamis, meaning heat and power. That's why we call the course heat power. And mainly we're interested in energy conversion, and primarily from the thermal form to the work form, and we'll talk about what that means in a little bit. Let's start off with the laws of thermodynamics. There are 0 through the second that we will consider here, and we'll consider the sort of tongue-in-cheek version of each one. The 0th law is two bodies in thermal equilibrium with a third body are also in thermal equilibrium with each other. So what does that mean? Well, thermal equilibrium basically just means they're at the same temperature. So if I have, let's say, 3 books in my office, okay, I know that book A and book B are at the same temperature, and book A and book C are at the same temperature. Therefore, book B and C are at the same temperature. In other words, they're in thermal equilibrium as well. Now, the joke version of this is there's a game. The first law you've probably heard of. It's the conservation of energy. Energy is not created or destroyed. It just changes forms. And this is something we'll explore a little bit more as we go through the course, because you probably don't really know how energy changes form. Yeah, you may know about the conversion between potential and kinetic energy, and that makes sense, but what happens in other cases? For example, what happens to all of the energy that goes into a ceiling fan? Where does that energy go? That's a good question. We can talk about that, and we will. The joke version of this law is you can't win. So there's a game, you can't win. Second law of thermodynamics, energy has quality, or a quality, that naturally degrades or disorder in the universe always increases. So this is the second law, and we won't explore it until after we have moved into heat transfer and then come back to thermodynamics. But the joke version of this is that you can't even break in. So there's a game, you can't win, and you can't even break even. So what are we really talking about here? Well, we're saying that you can't make something, well, there's many things that these laws lead to, very fundamental, very important principles that these laws are the foundations of, and not just in our discipline, but in many disciplines. So one of the results of this is that perpetual motion machines are not possible, and we have to be careful because some of you may think that they are, and that's okay if you do. I hope to increase your understanding of energy and power and all of these things and the nature of energy more specifically through this course so that you have some insight. There's probably a lot of inventions you've either seen or thought of, and you thought, well, I wonder why we can't do this, okay, or do that. I came across from some notes that I had written back when I was in probably middle school, and I wondered why we couldn't harness the power of gravity to do things. Actually, we do in a sense, but you'll understand that more as we go through the course. I thought that there was some way to just get gravity to make something fall continuously. Didn't really understand what I was even trying to think of at the time. Now that I understand energy and its nature a little bit more, I see how my lack of understanding at that point in my life prevented me from doing anything useful. So these are the rules. There's a game, you can't win, you can't even break even. In other words, we're not going to ever get out of something what we put into it. Now, in a sense, you do. It's just the way you get it out is not a way you want. But the universe works that way. There's nothing we can do about it. Okay, great. So you realize you've been tricked into studying thermodynamics. Where does this thing I'll abbreviate called Thermo, where does it appear in the real world? Well, here I'm going to try to excite you about the course and try to sell it. I'm not a real good salesman, but here we go. So it's involved in race cars and cold beer. Okay, there you go. How could you not be excited about that as the topic for a whole semester, right? I mean, we're going to sit and watch race cars and drink? Well, not exactly, of course. Race cars are a type of machine that convert chemical energy into mechanical energy. So that conversion is very important. In particular, it's done by taking the chemical energy, converting it to thermal energy, and then into work. And that conversion from thermal energy into work is a really important application of thermodynamics. Now, if you don't know what thermal energy is yet, or you're not sure exactly what work means, that's okay. We'll define them a little bit later. But race cars, okay? Race cars. Let's focus on the race cars. Cold beer. What do I mean? Well, refrigeration is another key area of thermodynamics. It's a key application area of this study, and that's the way we are going to apply, or that's what we'll focus on. But the laws of thermodynamics say a whole lot more about the universe in general. One of the things that they prove is that the universe had a beginning, which is a scary thought. Of course, the thought that the universe always existed is a scary thought, but we're not going to get into too much philosophical ground here. We're more interested in practical applications of these laws. So why does thermodynamics have a reputation for being difficult and therefore scary? Well, here are the reasons, in my opinion. There's some forms of energy that are probably new to you. Now, by now, you've probably studied some physics, and so you've studied potential energy, kinetic energy, the conversion between the two. You've probably used an energy balance and felt like there was more to it but didn't know what to add, so you just went along. So there are going to be some new forms of energy. I've already mentioned two, chemical energy and thermal energy. You probably have not done much with those in those terms in any other courses that you've had. You may have, but probably with a glancing blow, if you will. There will be a ton of new nomenclature and variables. If you want, go and see some of the front matter in your textbook, and you will see, I think it's 3 or 4 pages of symbols. There are a lot there. One of the things I want you to do as we go through this course is have your book out. You'll have your tabs. We are going to tab the book. We're going to correct some errors in it. But what I want you to do is also keep a highlighter by your desk, if you would. And when we come to a new symbol that you don't know what it is, or you know what it is and we start using it, highlight it. Okay? Don't be too afraid. We're not actually going to use all of the symbols that are in the front matter of the text, but we will use a good portion of them. And it gets really confusing because sometimes a symbol is used for 3 or 4 different things, and you got to know from the context what it is. For example, H. There's about 3 or 4 uses of the letter H in our text. So I'm sorry, there's nothing I can do about that. These symbols are decided by tradition, essentially, so we'll just live with it. Usually, thermodynamics involves the behavior of many fluids, so we have to know some chemistry-related type stuff. And I don't know about you, but even though I was a chemical engineer, chemistry wasn't necessarily my strong suit. More the mechanical area was. But we have to know something about chemistry. And the other thing, here's the kicker that gets most students, you have to use units. So I hope that, if nothing else in this class, I hope that you get a good grasp on units and what they are. I remember I really struggled with units. In fact, I distinctly remember sitting in recitation for one of my chemistry classes with the graduate teaching assistant right there, and I was asking him about units and how they work, and I was just really confused. I finally got to the point. This was a strange thing in my life. I remember it. I finally got to the point where I kind of understood them, but I didn't understand how you could just kind of mash them together and make other units out of them. I'll talk about that here in a minute. But when I finally just started using them, then I began to understand it more. So along the way, hopefully your understanding of units will develop a little farther than you have. Now, of course, you've had to use units to this point most likely in your coursework, and that's good.